Man, that took forever. Okay. So before we really get started in class material, a couple of housekeeping items. Number one, I did post a job up on the board. If you're looking for an internship here in Crete in manufacturing engineering, this is a little bit more mechanical based. There will be a lot of CAD drawings and some other decisions. There's a company, we've worked with them in the past. Everybody who I think, no. This was, yeah, we worked with them 2 years ago, but this is an opportunity for any of you who want a little bit of experience. I would go ahead and take that up. You can talk to me afterwards, you can email me. They're planning on making a decision this Friday, so send in your resume sooner than later if that is something you're interested in. If you're not interested, just ignore that piece, keep moving on with your life. But this is in Crete, so you wouldn't have to travel for it. They are flexible, and they have not taken an engineering intern from here before, so this will be a unique opportunity for us to get connected with this company. It'll be interesting. I'll certainly be involved in it more than I probably need to be, but that's just because I can't help myself.
What company is it?
Interlux Siding and Windows. They do fiberglass casings for windows, and they try to make it energy efficient. Hand build all their stuff. They're on the other side of the train tracks right behind Bungie. I can show you where it is if you really want me to. But yes, it is definitely more manufacturing based. Do realize you're in competition with each other for this job, so good luck. This is where I can't play favorites, and originally was like, well, I could hand select a student and send it to you. And I'm like, well, I'm gonna pick a few students and encourage them to apply, but really I don't want to play favorites here. None of you are my favorites. None of you, absolutely none, except for maybe Walker. Okay. Oh, and Jacob. I like Jacob. Maybe. Nah, it's just Walker, really. Sorry. Dang it, that's on YouTube. I always have my worst moments when I'm recording myself. That goes on the internet, and then it never goes away. It's like a meme. All right, second piece of housekeeping is I want to talk a little bit about your final project. I haven't given you anything official about the final project. Some of that is because I'm still formulating exactly the components that I want. I have 95% of what I want from you I have in my mind right now, and that's what I'm going to be telling you, okay? It's that other 5% that I'm still like, well, do I ask about this? Do I ask about this? Our plan right now is this is going to be a class time where we talk about ODEs, how to solve them on Python. Next Tuesday, we're going to be meeting for the week before finals. I will have a brief discussion on feedback systems. This will be very brief. You will then have the rest of the class period to work on your final project. Next Thursday, you will have all of the class period to work on your final project, okay? And then we'll have finals and you will present what you've come up with, okay? What I'm expecting for you for your ultimate hand-ins, this is the 95% I know that I have worked out, is I'm going to be expecting, first of all, you're going to have to collect data. Okay, what we did for project 1, you're doing it again. Those photoresistors that I gave you, I didn't give you any information on them. There's a reason for that. I don't want somebody to hand you information and you just think like, here we go, this is good enough. You have to go out and collect the data. What data are you collecting? Well, you need to know what the transfer function is going to look like. And just like the last project, you are collecting data in order to come up with some kind of formula that says, okay, for this amount of light intensity, we can expect this kind of thing. Now, how are we going to do that when we don't have a good way of measuring light? Well, that's a great question. That's the 5%. I'll have it figured out by next week. Because I know there are ways of like using a camera to figure out what overall is the light intensity, but I don't want to play with that yet. I'm still working on that. I will give you an answer by next week. I might have to buy something. But we will come up with a transfer function, and you will be expected to take many measurements and figure out how that transfer function works. How does light convert into resistance in this component? Once you know what that transfer function is, you then need to plug this into a feedback system. Okay, what does the feedback system look like? Well, for the feedback system, what you have is you're going to have this sensor is providing information about how quote-unquote good the system is operating. Now, I'm not going to have you plug it into a light socket and actually control the lights in the room, which would be an awesome project. And I might have thought about doing that, but I also didn't want to get in trouble with facilities again. So instead, you will be producing a feedback system as if it were a lighting system for a room, okay? And we're only going to control a couple of LEDs, but in reality, you can plug this in and you could control a much bigger lighting system with something like this. You could plug it into a street light and have this be a street light operating system where it is sensitive to the lighting conditions in the environment around them. For a little bit of light, maybe it shows up as really bright. You know, just a lot of different factors run into what you're doing here. But for your feedback system, you're required to hook up a sensor. The sensor is the photo resistor that I gave you. You're already given that. Feedback from the sensor goes into a system where it then dictates how much power gets consumed by the LEDs. Okay? And as a part of this process, you will have to program how the sensor information is converted into a command that gets sent to the LEDs. Okay? Now this all looks like some kind of a block diagram. Oh, wow, that's another thing you have to hand in. Now I'm not looking for, here's a theoretical block diagram. I want a block diagram of what you actually did. Show me your transfer functions on a block diagram. Give me an as-built configuration. Don't give me a theoretical one. So your block diagram, I'm not going to ask you for it until it's done, but I want to know, what does this look like? Okay? Now these three pieces of information go into your presentation and they provide evidence for you designed this well. Okay? As we talked about earlier, the whole goal of your paper was I want you to be able to prove you designed this well. Here I'm not having you write a paper. Okay? I'm going to try to give you feedback on your papers over Thanksgiving break. I'm planning on overworking myself this break to give you feedback on those papers. But I am asking for a presentation, okay? Presentation, I will basically be sitting down for the presentation and saying, you are crafting an argument saying that you designed this feedback system well. In order to give your presentation, you have to show me you understood something from this class. Okay? We got to talk about transfer functions. And that's something that I'm going to be specifically looking for. You can't just say, here's the formula for the transfer function, we're good. I need you to give me evidence. Prove to me that whatever formulas you come up with are validated by the data you collect. You've already done this once. You're just doing it again. Okay? Second, after you've proven to me your transfer functions, here you're going to have to solve ultimately what your overall ODE is. Okay? You're going to come up with an overall ODE. This may be a second order differential equation. It could be a first order differential equation. It could be not even a differential equation. But you'll have some way that you have to solve this such that you can calculate output based on input. Okay? And for this, again, here you're just showing me, here's what an input function would look like. Like here's a normal daily cycle of lighting in a room. When this normal daily cycle of lighting in a room happens, here's a graph of what you can expect the power consumption to be, okay? Now I'm not going to be going around and seeing like, well, is the condition of his input statements valid? That's not what I care about. I want to know, have you identified outcomes? For this type of a system, are you going to focus on power consumption? If you are, that's your output. You have to come up with all of your equations to determine power as an output of the system, okay? Or the flip side, if you don't care about power, if you only care about lighting in the room, you're going to have to make some assumptions to do that. But if that's the case, then that's your output, and then how do you show how the lighting changes as the input is measured? Okay? So really, this is a little bit open-ended, which is, for most of you, giant frustration, because I'm not spoon-feeding you anything. I'm just saying, here's what I'm looking for. I want you to solve an ODE for me. I want you to provide graphs. And I want those graphs to show, here's what this system does based on these input conditions. Okay? That's what I want to see. That is the entire second part here. So first part, you need to explain your transfer functions to me. You need to define them. You need to prove them. Second part, use the differential equation. Here I would show the differential equation in your presentation. You don't have to show how you solve for it, but I would show it. And then talk about the output. Talk about the graphs. This is the fun part of any presentation, okay? You can give me graphs, you can show me, here's what I would expect this system to do given this range of inputs. That's what I want, okay? All right, and lastly, I am going to be expecting a block diagram. This one's probably the easiest of all of these. Oh, and then, no, I guess lastly, is I am expecting a physical item. So you have to present an object in class, and then you have to be able to, well, we can adjust the lighting in the room, and you have to be able to show me that yours changes, okay? I don't care if that means you plug it into your computer and do a measurement, or you're using your Raspberry Pi, I guess. If you just have your Raspberry Pi spit out like, oh, here's how much power is going into this system, that's enough for me. That's all I care about. Okay. Any questions right now about what I want from project 2? Hey, Shingy. Okay. I will give you something more formal on Tuesday. As I said, I'm still trying to figure out this piece, which is frustrating me to death. Because I don't want to have to spend money, but at the same time, sometimes it's necessary. All right. I'm going to assume you watched the video that I told you to watch, because I haven't given you a ton of homework in this class, and when I do give you homework, I expect you to do it. So we're just going to keep moving as if all of that has already been watched. If I go ahead and pull up the equations that I had written out from last class, Okay, so this is what I had. I had y1, negative k2, c, this is k2, negative c, negative m, K1 plus K2, negative C, negative K2, C, 0, 1 times d dt, negative 1, 0, 0, 0, 0, 0, 1 times d dt, negative 1, 0, and then 0, 0, 0, 1 times d dt, negative 1. Okay, and this was y1, y2, y3, y4, and y5. So when I took this matrix and I multiplied it by y1, y2, y3, y4, and y5, I got K2 xi2 minus mg, negative K2 xi2 plus K1 xi1 minus K1 x0, and then the rest of these were 0. So this is where we left off last class. I am not going to go back through and rederive what these mean. Go back to your course notes if you don't understand this. Be a really good review. Hey, did you see the picture of me staring into the camera? Did you even send it?
Yeah, I did.
Shame on you, Nathan. Check your phone.
We were watching downstairs.
Because why show up to class when you can watch class from downstairs? That's fun. Okay, so this is what we have. Now, that's kind of gross. This isn't exactly the form that we want to have this in. So instead what we end up doing, if you watch the video, what we end up coming up with is we have to rearrange this a little bit. We want our output from this system to be something that we can just plug into an ODE and solve it. Okay? How far over do I have? Oh, I only have till here. There we go. Man, this marker sucks. I'm gonna go get a mirror marker. I'll buy all these markers. Fresh Expo marker. Okay, so we want something nice that we can take and plug into an ordinary differential equation. So what we will have for the ODE solver is we're going to have to put in 3 different things, okay? Every ODE solver takes 3 different pieces of information. Number 1, it takes the variable equations. Okay. Number 2, it takes the differentials of those equations. Need to know what the differential is. And number 3, you also need to know the initial conditions. Okay. So here, if we know all 3 of these pieces, we can plug them in to a differential into an ODE solver, and we can solve them. But we have to know these 3 things first. Okay? Now, we have all of our equations already written out. It's not in a nice form because, I mean, we do have differentials in here. Gross. Yuck. But we do have them. We do not have a list of the differentials of those equations. And we haven't even talked about initial conditions. So, ugh. We got to start somewhere, okay? Let's start with cleaning up the equations, okay? Now what I'm going to do here is I'm going to have a set of y1, y2, y3, y4, y5, and then have them equal to something. Okay? That's my goal here. From the differentials, I'm then going to take the differential of each of those equations and have them equal to something else. All right? Now you'll notice some of these I can't even put in here without including differentials. So let's we gotta change the way we see this. Okay. Now the first thing that I'm going to do is I'm going to identify what is the highest order. So for this equation, does anybody remember what y1, y2, y3, y4, y5 are?
x1, x dot 1, x2, x dot 2, x dot 2.
Thank you. Okay, so we've got, that's the one piece I didn't have. What we have here is our highest order. What is our highest order out of these 5 variables? X2 double dot, right? So what we can do is, honestly, I'm going to start by eliminating this variable. Okay? Well, yes, all of these are true. I'm going to start by getting rid of it. We're going to put all of our equations in terms of these 4 variables. Okay? This one is going to be the only one that requires a derivative. Now, here, we can also do that with the highest order for x1. We can put all of our equations in terms of y1, y3, and y4. We only need, what, 3 different equations at that point? And then we'll have differentials of those. Oh, no, I think I'm doing this exactly wrong. Yeah, I am. I'm doing it exactly wrong. Never mind. I'm talking about step number 1. So when we go to step number 1, okay, first thing we do is we identify each of the variables that are not the top orders. Okay, so here we've got y1 is equal to something. y2, well, we're going to ignore that. y3 and y4. Okay? For our second step, where we focus on the differentials, here's where we get into y1 dot is equal to y2 dot is equal to, no, I'm doing that backwards too. y3 dot is equal to, and y4 dot is equal to. Okay? So we've identified, here are our top differentials. They're the highest order differentials that we have. We then go and say, okay, y1 dot is equal to y2. y3 dot is equal to y4. y4 dot is equal to y5. And we don't take a y5 dot. We don't take a y2 dot. Neither of those show up. Because neither of those show up, we're not really going to end up with those equations. Right? So what I'm going to do is I'm going to go ahead and take this one and this one, which right now only show up here, and I'm going to solve them here. So what is y2 equal to when it comes to all of our equations? Where can we pull out a y2? We have 3 places where a y2 shows up. We can take any one of those 3 equations. Okay? I'm going to go ahead and pick the top one. Hold on. y5 shows up only here. I'm going to pick the second one for y2. So I'm going to solve y2 in terms of this second equation. So here we know negative c times y2 plus k1 plus k2 y1 minus k2 y3 plus c y4 is equal to this expression here. Negative k2 xi2 plus k1 xi1 minus k1 x0. Okay? I know I wrote out of the bounds of where I'm at. Just going to move the camera a little bit. There we go. All right, we can solve this in terms of y2. All I have to do is move this over to this side and then divide by negative c. So, skipping a step here, y2 is going to be equal to k1 plus k2 divided by c times y1 minus k2 over c y3 plus y4 plus k2 xi2 over c minus k1 xi1 over c plus k1 x0 over c. Okay, so we've now solved y2 in terms of all of these factors. Okay? Now the nice piece is we can plug that in right here. Because we know that y1 dot is equal to y2. We know that this is what y2 equals. So we can just plug it in right there. And I'm not going to rewrite it again. Okay. y3 dot is equal to y4. Well, y4 shows up in both of these equations. It does. Right here for this equation, and it shows up in the other one. So we're not going to get rid of that. We need that one to be there. But we can solve for y5. This equation has y5 in it. No other equations have y5 in it except for this one here. So these are the only 2 equations. We're going to solve for y5 using the first equation. So here, if I pull out the y5 first, it's negative m y5 minus k2 y1 plus c y2 plus k2 y3 minus c y4 is equal to this piece up here, which is k2 xi2 minus mg. Okay, if we solve this in terms of y5, all we do is we move these variables over here to this side, and then we divide by negative m. And what we end up with is y5 is equal to negative k2 over m y1 plus c over m y2 plus k2 over m y3 minus c over m y4 minus k2 xi2 over m plus g. And now this is the equation we have for y5. If we plug it in right here, we now have the differential for that variable. Okay, so yes, we have 5 different variables. But we're only going to end up using 3 of them. Because we only need 3. The reason why we only need 3 is because the only times that, well, this is the highest order and this is the highest order. And because those are the highest orders, we come up with functions in terms of them so that we have ordinary differential equations that we can solve. Okay? So, 5 variables, we boil them down to 3 and their immediate single derivatives, which are these. This is a little bit easier to solve than a 5 equation problem, but this is what we now know. Well, what is y1? Well, y1, it's y1. y3 is y3. y4 is y4. So our number 1 equations of variables are the subbracket y1, y3, y4. Simple. It's the ODEs where things get a little bit more complicated. Okay? It's where we take these equations and we condense it down. You'll notice we removed this one because we don't need it, and we removed this one. Yeah, we removed that equation because we don't need it. We ended up with only the others. So our list of our ODEs are going to be equal to this equation, which corresponds to, this is equal to y1 dot. So this equation for y2, I'm just going to write y2. Y3 dot is equal to y4. So all I have to do there is y4. And then this one, which is equal to y5. Write out the equation for what y5 is. Okay? We now have 2 pieces of information that we have. We have the equations for the variables, which is just us writing out the variables. We then have our differentials of those variables, which is our equations that we have, these 2, and then this one here. The last thing we need is our initial conditions. For each one of these 3 variables, we have to identify what is the condition that happens at 0. Okay? We can assume that the vehicle starts, I don't know, you can assume the vehicle starts anywhere. With this vehicle suspension model, if you assume they're all starting at 0, you're basically assuming that everything is compressed and it's touching the ground. Which means that your initial conditions are going to go like this. I mean, fun. You gotta identify some reasonable initial conditions here. Which, because I'm trying to get out early today, I'm not going to do. What you could do, though, for identifying initial conditions is actually go out and measure what is the original height of the axle? What is the original height of the bottom of the vehicle? You go out and measure those, you have your initial conditions. Those are just numbers. Okay, we go out and assume XO, which is ground level, we assume it's 0. Just numbers. Okay, all right. Now this is a little confusing, so let me step through this one more time. Hopefully, if you didn't pick this up before, you can pick it up again. Why did we put together 5 matrices and then cross out 2 rows? Why? Well, this is the way that I think. We took all of our equations, we took every variable, we identified it in terms of y1, y2, y3, y4, y5, okay? We did that initially. We got rid of all of our differentials. To me, that makes sense. From this, we can then put together a matrix. where 3 of those equations do have differentials in them. We can't solve this matrix as it is because they have differentials in them. There's no nice way of doing it. But this is how I like to think about it. It's an organization. Now, if you can skip this step and go straight to these 3, great. Go for it. I wouldn't discourage that. I'm showing you the way that I think, the way that this makes sense to me. I put together this matrix because I like having all 5 of my equations nice, neat, everything together. From there, I know that the 2 highest orders are going to be taken out because I don't need them. Why don't I need these 2? Because when it comes to the differentials of those variables, they never show up. We don't have a y5 dot and we don't have a y2 dot. So they're not going to show up in my differentials of variables here because I don't know what they are. I don't even have equations for them. So I take out the highest orders. Once I've taken out the highest orders, everything else is just a matter of solving for the equations. Okay? And you do end up with this function, well, this function, and this function. Those are your only 3 differentials that you have. The other 3 equations for your variables are just simply your variable names. Now you will notice, because of the way that we set this up, none of these have y5 or y2 in them. Because we solved for them. So because they don't have y5 or y2 in them, we only have a system that uses 3 variables. Okay? Now, if you did end up with, there was a weird y5 in this equation, and we had to do something, what you end up doing is you end up having to include another variable. Now, it doesn't have to be y5, it could be a y6. But it's something that where you have to know what the differential is. You have to be able to include it in there. Sometimes you have to do math like that to get rid of the variables. But once we have these 3 equations where they only consist of y1, y3, y4, we're then good to plug this into a solver. You plug it into Python, we're done. Okay? As far as identifying initial conditions, here's where you got to choose something that makes sense for the system. My initial conditions were, where is x1 relative to ground? Where is x2 relative to the ground? That's what I want to know. Here, because we're dealing with 3 variables, we also need to know what y4 initial conditions is. What is y4? y4 is what is the upward speed of the mass at time 0. We have to know that. We don't need to know what the acceleration is at 0. We do need to know what the speed is, okay? And that's just because we are dealing with a second order differential equation there. It does require 2 initial conditions. Just comes out the math nicely. So if you assume that your vehicle is traveling, I'm off camera. If you assume that your vehicle is traveling, pardon my terrible drawing for a car, and you hit a bump, before you hit that bump, your vertical speed is 0. Now, this function for the bump is going to be a change in x0. All we do is we change x0 to equal that formula. And then we have our functions. We solve it from that. Everything goes. Okay, this is our input. You could also assume what happens when the ground is flat, meaning x0 is constantly 0, but your vehicle just falls off of a semi-truck. Okay, you're driving down the road, a car's being carried on the back end of a truck, it falls off. You start at some height above ground, and this comes into contact with the ground. Now, some of the model doesn't exactly work well because the model assumes that the spring is actually connected to the ground, which means that the model would assume this tire is mounted to the ground. But you could do this from the moment that it hits. what is the balance of the vehicle going to be as it leaves the back end of this truck? We can do those calculations. Okay? So there's a lot of versatility we have in coming up with a system. By understanding the system behavior, we can do absolutely anything to this. Austin, you can have an equation where you plug into this. What happens when you jump up and down on the front end of the car? How's it going to move? You can figure that out using these equations. All that's going to change here is you're going to be adding a force to this one right here. Okay? We're adding Austin's weight of him jumping off the car, and that will be a function. You plug that in, we still have the same equations. The math still comes out the same. The only place this shows up now is here. Solving the same way. Okay? This is an incredibly versatile method of modeling this system to get the final result. All right, any questions? Okay, get out of here and go have a good Thanksgiving. I'm not giving you homework over Thanksgiving. But be ready to come back and work on project 2. And yeah, I may need to create a video on how to do all of this in Python because we don't have time right now. I'll do that next week.